I'm Javen. I believe you can hear me. So my research interests include causation, AI, mind, and metaphysics. So this is the AI causal AI group that I'm leading. I created. You can see at the moment we're focusing on causal large language models, agentic AI, and other causal topics. Also, I'm leading a responsible AI research center where we have 4 directions. The last direction is also about causal AI. As human beings, we know, and we are. Hence, I will use that as 3 lenses to examine the advancement of AI, and also how can we, as a human, to reflect ourselves from what we have learned and taught AI. So let's start with the first doing part. Right? The doing part is what we are often very familiar with. I guess everyone has been using AI now, right? Nowadays, there are a few different AIs. So all the stuff your AI has been doing, although amazing, right? ChatGPT and other things you use or you build, they are called narrow AI, because those are the AIs that can only do the task that you trained it for, right? Or maybe a set of tasks that you prepared it for. But you see, if you have 1 billion different tasks, you have to build maybe 1 billion AIs. That takes forever, right? You don't live forever, and it costs you a lot of money and effort as well. That is why the whole world designed something called an AGI. So AGI is a one model or one algorithm can solve all problems. And that's very debatable how many years from now that we will reach AGI. But once you reach AGI, then humans are largely free. But there's something beyond AGI, because AGI is normally supposed to be performing at the only human level. So it just needs one algorithm or one model, but it's no smarter than human. Okay, it can do what a human roughly can do. Then there's something called super intelligence, and it doesn't have a great definition, but according to NVIDIA's founder, Jason Wang, right, what he believes, his concept of super intelligence is an AI that is 1,000 times smarter than human. Now think of that. If you look at IQ, right, Einstein and many other super genius, whose IQ may be only 2 times higher, right, than the average person, which makes a big difference already, right? If you think about Elon Musk, maybe 50% higher than the average person, which already gives a huge advantage. Then you think about a super intelligent AI that is 1,000 times smarter than you. So this is the world, the future that's hard to imagine. And along the doing line, we just want to show you some of the stuff that my team has been doing to show what the kind of things that AI nowadays can already do. So this is our vision language model in-house. You can supply any images. Our AI model will be able to answer any questions. You can ask anything. It's all just like a ChatGPT. For example, you can ask, what's going on with the building, why it's collapsing? The AI will provide not only the answer, but also chain of thought. Right? It's likely because earthquake is collapsing. You can also ask how much or how long it would take to repair it, right, and to fix it. This is a demo that you can ask questions about the image. What's the baby's holding, right? Is a spoon, a knife, and what's that for? What's the candle for? Right? Well, it would actually know. We also have AI agent where you can ask it to create, it can understand your question and formulate it as a mathematical problem and write the code for it and execute the code, return the result. And if you're not happy with the result, it will refine model, run again and come back with a better solution. So this is the process. After understanding what you want and generating the code, execute the code, return. In this case, it's you want AI to come up with some more healthier diet. You ask it, maybe it has to be within certain calorie, so you're not getting too fat, right? And more than certain amount of protein, so you have enough nutrient, within certain budget. So you would just create that for you. And we have done many different applications. For example, in viticulture, grow grapes to make better wine, grow better crops, wheat and sorghum barley, and use AI to predict how fire will spread. Australia has a lot of bushfires. Use AI to predict wind energy, better harness wave energy. We even use AI to discover new energy materials and also drugs as well. So we won at the Europe's 2023 Open Catalyst competition using AI to discover new energy materials. So the past year's winners were Microsoft, Tencent, but that time we won. So, and we use AI for medical, for mining exploration. So AI can do a lot of things, right? So that's the part of doing. Well, what now? Think about something else. What AI cannot do? What do you think? Any idea what AI cannot do?
I think AI currently is only limited to vision and language. For other, maybe sensing or smell.
Actually, it can. So there are smell sensing robot, which actually somehow simulate the human tasting buds. So not only tasting bud, but also the nose as well. So because they are essentially, it's just sensing. So if you have the hardware to do sensing, and then AI is the brain that can process it. And also AI can take your brain signal, EEG signal, and to understand your intention. So for someone who don't have maybe arms and legs, they can use the mind to control a car or robot. And that's because AI can read your EEG from that to know what's going on. So, but there are things AI cannot do at the moment. What else do you believe?
There are some very simple issue-based questions where the language does not play important role. Okay, so you mean the whole AI, or you mean just only foundation model, vision language model?
Whole AI, even AGI.
Okay. For example, writing a very interesting novel, something like that.
Oh, AI can do that.
You can write a lot of exciting things, but not really interesting.
So, can AI feel? Can AI love? Those are the things AI can't.
Recently, they claimed that they can also understand the emotion and has.
That's different. That's understanding is not feeling.
Okay.
So we're going to go next to the understanding part. But next question is, what jobs do you or your students plan to do for the next decade? You can hold that in your mind, right? You don't have to answer me. Hold that in your mind. What jobs do you or your students or your children want to do for the next decade? Okay. Then think about where they still exist. The jobs the perfect job, dream jobs that you or your kids have in mind. When they grow up, where these jobs still exist in the time of AGI. So the world is changing so fast, right? The old way of life and work will change with it too. So information and knowledge, they used to be slow and expensive, right? It takes about 15 to 20 years to train someone to be a good technician, or maybe 20 years of training to be a doctor. But now with AI, everything gets fast, cheaply. And so are the skills. So that's a major problem as what's the future role for the education organizations? Because all the education organizations are doing is to transfer knowledge and skill, which actually are going to be cheaply available because of AI.
You mean skills in the cyber world or in the real world, in the physical world?
Both. Even in physical world, you have robots now, right? In the future, robots gets better and better. So, and as you mentioned about knowing, right? You mentioned some people argue AI can already know and understand other people's feelings. So let's move on to the knowing part, understanding. The first question is, are large language models like ChatGPT and others, are they just talking parrots, or do they truly understand and grasp human interpretable concepts? In other words, right, by training an AI to predict next token alone, will that be enough for the model to learn human concepts? On the surface, the answer is no. And the whole world is divided, right? All the big names, they are in two camps. Some say, oh, you predict the next most likely token or word. But doesn't mean you understand it, because there's no training objective have understanding involved and no knowledge base involved, right? No knowledge graph. It just predicts whatever has the highest probability next. So that's one camp. The other camp says, by experimentation, those large language models seem to understand space and time and entity and relationship, but by experiment. But the first camp will say, well, they are faking it, right? They give you good answers, seem to understand, but may not really understand. So before we reveal the answer, right, we just show you, is that possible? If when you are trained for something, would you be able to acquire something else? Think about if you go into a gym, right? Go to a gym to do exercise, to push the bars, right? Is the purpose just to push the bars? Of course not, right? By pushing the bars, you want to get the other benefit: healthy body, more muscle, right? More strength, and some people just maybe go for the looks, right? Better looks, so more attractive, right? But it's never about just pushing the bars. When you go swimming, is your purpose just to develop another way of transportation? No, that was not for transportation. Swimming is also to get healthier, right? Or maybe lifestyle. So that gives us some hint that maybe, right, when you were trained for something, you may develop something else, right? So we just uploaded the paper a few months ago, our archive. We didn't do any PR work. The paper has a catchy name. It's called I Predict, Therefore I Am. And it answers, is next token prediction enough to learn concepts from data? Then a Japanese philosophy group, they saw our paper and they love it so much that they post on the Japanese Twitter. So, because philosophers, they kind of know that by reciting some poetry or legal document, you are not just doing reciting, it's kind of changing your internal structure of your knowing. But they don't have the mathematics to prove it, right? They kind of knew or guess so. So we did the mathematical proofs. The reason we could do that because we're good at with the causal AI, especially discovering causal latent variables. So we showed in the paper, the last layer of the large language model, right, just by training to predict next token alone, nothing else, just a simple one. The last layer of a large language model has to be a linear mixing of the log probability of human concepts conditioned on the tokens. And you don't need to tell the model which words are the human concepts. No, the model will just learn by itself, will figure out by itself by predicting next token. So this shows what? This shows AI can understand. It is not a token parent. And this is by mathematics, by proofs, right? We have many pages of proofs. This is not by just experimentation. Okay. Then does AI believe everything humans teach? You may think, oh, we are the makers of AI. Is that so? So let's examine 3 scenarios. The first one is AI with a teacher, a typical supervised learning, right? If you just take a very simple neural network, like a multi-layer perceptron, it already have creativity because it can, even if it's just trained for MNIST data, which is about handwritten digits, right? A picture of that, you want AI to tell what's the number is that. Someone did an experiment, and Hinton mentioned that. Maybe Hinton himself did that too. They purposely poison the training data label. They put a 50% wrong label into the training data. And you may think, if the AI was given the wrong answer, right, the wrong labels, then the testing error would be 50%. Right? Because you get 50% of wrong labels. And they did it in a very careful way so that by averaging them, you cannot averaging out those wrong labels. So it's not those trivial self-correcting one. No, it's a very sophisticated way to poison your data labeling so that normally you would think the testing error would be 50%. Guess what? The testing error is only 5%. So the AI does not always believe what human teaches it. It's like a smart student, right? A very clever student actually knew when and what the teacher was lying or telling something wrong. The student would absorb what is right, or discard what is wrong.
So the model is not trained from scratch. If you train from scratch on MNIST or C-Cartoon, you give 20% knowledge labels, wrong labels, then the test accuracy is really like that.
No, so it is training from scratch. So it is you put 50% wrong labels, and it's in across all classes. The testing error is not 50%; it's 5%. There are good reasons for that too, but it's.
I'm expert of label noise learning, and we tried this so many times.
Yeah, you can try. Hinton has a talk on this too, so you can check his interview. He has an interview on this. Then if we look at the AI without teacher, so reinforcement learning is an example, right? So it doesn't need a teacher. It always needs is the environment gives the feedback. So because often you don't have all the right answers prepared, right? So, but it doesn't need it. So some of that has it's like a word model or model-based RL would have a word model that kind of predicts how the word works. So in this case, it does not need teacher. But of course, the large language model you have seen is a mixed. Often it has a word model and also has certain level of supervision.
I'm still interested in what's the model and what's the label noise have? It's a class conditional noise or instance dependent noise?
I'm not sure about the detail. That's I've taken that from Hinton's talk. So
Hinton is not expert of label noise learning either. That's the issue.
I guess maybe it depends on where you use stuff. Maybe if you use early stuff, maybe it's more better.
Because it's not taking anything. It's too simple. How? Because
there's some locality. So if you in some locality, right,
yeah.
that you could have more.
No.
Right.
The most possible reason is that the model is too simple, and also sometimes if you inject a lot of label noise, but it's 2D data, because you have too few features. Even if the model is very complex, the model can, because it does not by using neural network or any complex model, you can still only fit Lipschitz continuous function.
Yeah. So let's discuss maybe that offline. We still have a lot to cover.
Okay.
So we are still just halfway of the talk, not yet even halfway. So then what is AI's mind? If we think about knowing, right, we know what is human mind, but what's AI's mind? Well, model weights, or someone may say it's representation, right? But then what is human's mind? Human actually has a tree of mind. You have the surface consciousness, you have your subconsciousness, you have your unconsciousness, the things that you don't know even there. The tree of mind also deep down has something called a collective consciousness. And further, human has built-in causality. And human prefer to jump into conclusion about even something when it's not causal, they would jump in to say, oh, that's causal. So here's one example, it's known as a Simpson reversal and paradox. There's two types of treatment for kidney stones, right? And treatment A and B. And the numbers are the success rate, the recovery rate. It has a reversal effect is if you know what is the treatment, if you know what is the stone size, right? So condition on the stone size looks like a treatment A, recovery rate is always better, right? So 93 vs 87, right? But if you don't know the stone size, looks like treatment B is better, 83. So the question now is which treatment is better? Regardless, knowing or not, there is one treatment is better. So now, what do you think? Answer me. Maybe put your hands up. Who think treatment A is better? Put your hands up. You think A is better? 3 of you, okay. Then who think B is better? So in this case, I can't say people online, but well, actually most of you are correct here. So 3 of you, right? So the ones put hands up. So in this case, A is better treatment. But why we have a reversal effect? That is because A is much expensive treatment, and so when you have big stones, you often go to A. But if you have tiny stones, doctor thinking you just drink more water, jump around, it will just heal by itself. So for the simple symptom, even if you don't have treatment, the recovery rate is higher than the big stone case, even you receive the best treatment. So, and if you look at it carefully, the data is not balanced. If you do some balancing, this reversal effect will disappear. Now you're going to see the paradox, right? Because one example alone is only reversal. Now with the same numbers, so you cannot say, oh, Javen, you have changed numbers. No, the same number and there's no noise. 2 drugs, A and B. And they are to improve your heart condition. Now, which drug is better? So 2 types of blood pressures, lower or higher. Put your hands up if you think, say, A is better. And put your hands up when you think B is better. Okay. Why do you think B is better?
Because for the size of the stone, it can easily detect that it cannot change rapidly. But for the blood pressure is a dynamic variable. This is already known in medical science.
It wasn't that reason though. What wasn't the wrong answer is correct, but it's not the right chain of thought. The reason is here is the causal graph is different, although numbers are the same. So for the kidney stone, the doctor would decide the treatment based on the stone size. So the stone size are the cause, are the parents. Whereas for the drug case, in the kidney stone case, if you observe the stone, which is you block the back door, so that whether you balance or not, it doesn't matter if you observe the stone. So in that case, you should always condition on the stone, on the stone size. But in the blood pressure case, if you condition on the blood pressure, then you are making the wrong choice.
Mention that the drug affects the blood pressure. Maybe the drug is good for heart because it can reduce the fat levels or something like that.
So it's the drug's main function to reduce heart attack is by lowering the blood pressure. So when you observe the blood pressure, you are blocking its effect. So you are saying now you cannot lower the blood pressure. So that is why in the second example, you should not condition on the blood pressure. You should look at the marginal alone.
Maybe I can change the heart attack to like a sugar level. The drug can control blood level, but you have two drugs. One is better if you know the blood pressure for the sugar level, but one is better if you don't know the blood pressure for the sugar level. Even in that case, people still prefer treatment B.
So
what I say is already known and it's fixed in medical science. If it depends on something like a gender or like the stone size, that cannot change. That is not so dynamic. It's basically static.
No, your scenario is different from this scenario. In this scenario, is the causal effect. When you observe variable, you are blocking its effect. So you don't understand the causality. If you observe variable, you are blocking its effect. So if you condition on the blood pressure, you are blocking the drug effect to influence the blood pressure. So you can change that with sugar too. If something about diabetes and sugar.
Just the drug, blood pressure, and the sugar level. Because in that case, the drug is good for the sugar level, not because it can reduce the blood pressure. You don't have you don't have. For example, you don't have the edge. You don't have the edge from the blood pressure to the sugar level. Even in that case,
that is you are changing the causal diagram. So here is where if we're talking about this causal diagram within this setting, you have a drug that lowers. If you take the drug, it lowers the blood pressure, so that it reduces the chance of heart attack, right? Which it would naturally have this causal diagram. In this case, if you know what is causal diagram, you know whether you should observe the variable or not observe the variable. So the Simpson paradox, you can check online. It's a very famous paradox.
I know this.
You know Simpson paradox.
I know this. I also studied this a lot, and I talk this about to the medical science people. And what I talk about is just their understanding. They don't believe this one. But they believe because blood pressure is also very fluctuated a lot. Even like within a few hours, it can be up and down, right? So they believe that you cannot.
You can change this to something else. You can change this to non-medical. So if you have this on the right hand side, this causal diagram, you should always not to observe the third variable. So it can be real estate. It doesn't have to be medical. So in this case, the Simpson paradox is for it doesn't have to be medical, but it's based on.
Because the original example is medical, especially for the two examples.
So I guess you're providing an alternative explanation, but not the causal one, right? So that's you're saying, and you seem not understand the causal explanation. right? So that's okay, because otherwise we have to move on. Otherwise we're running out of time. You can check up on Juniper's and many other people's discussion from the causal perspective. So so what causality brings you mainly three powers. The first power is deeper truth. So it can provide you the cause, even root cause, and can reveal the right choice when there's a spurious correlation. For example, even in sympathy paradox and many other cases. It can also uncover latent variables, so which are the variables you never get to see, but within certain mild conditions, you can recover uniquely the variables in the middle. The second power is, you think, because causality essentially is a way of change, right? You think about cause effect is you change something, what else change with it. So that when you see a diverse data sets and tasks, then you can model them as shifting, changing among them. So that gives you a better perspective, help you to better generalize to new scenario. And the third power is, it gives you the power to shape the future rather than just adapt to the future. So, and that's one of the key difference between causal reinforcement learning versus non-causal reinforcement learning. So here's, and causal AI is often modeled as structural causal models, but we probably would not have time to go with details on this. But a few key messages on this slide is intervention is different from conditional observation, conditional probability. Intervention, a hard intervention is when you intervene a variable, you chop off its parents' links to it. And also you can have soft intervention, but all interventions changes the distribution. So whereas your correlation-based model assumes your distribution does not change by your own choice. You can have external forces, right? So dynamic models change, but this is not by your own choice to change it. And the second key message is that counterfactual reasoning is different from intervention. So counterfactual reasoning means something already happened, right? You observed certain facts. Then you want to ask, what if something else, right, happened differently in the past? What else would happen? So to do counterfactual reasoning, you have to reconstruct the past first, then intervene in that past. Now it's a simple test here is to say, if you have a latent variable z, right? The z variable are the variables you never get to see, and x is the variable you get to observe. Could be an image or text. Could be a large language model, right? That output the tokens, right? Or visual language model output as image, or diffusion model. Assuming, and from z to x is MLP, right? Flexible nonlinear MLP. Can you, based on the x alone, can you uniquely recover the latent variable z? The answer is no, you cannot uniquely recover it. The reason is all these three models here, we put a different factor in front of the z variable or adding an edge, right? Or even change the edge direction. All the changes can be absorbed by your MLP because your x is a function, is a nonlinear function of your z. So any modification on the z can be just absorbed by your f function, by the MLP. So that means you cannot uniquely recover it. However, if you have external variable, like the u variable here, which is often known as a domain variable, or it can also be a time index. If that provides some changes to the generating process, then you can uniquely recover it. So we'll go through it quickly. So we have a few papers on it. One is when the relationship among z variable are linear, so that's the first paper we proved that you can uniquely recover. So here is only u is observed, is the domain index, which domain or task or time. X is observed. The z and n are all non-observed. But people say, oh, nonlinear is too restrictive. Sure, so we did something with so we extended to polynomials between z. Then people say, oh, we love MLP. So then we extend to even among that, they can be MLP. in all the three cases, from Z to X is MLP, is nonlinear. We also saw causality from another perspective. You see, when you look at the domain index, you only see the after effect. So different domain is different after effect. But what if you can see both before and after effect? It's almost like you do an intervention, you get to see what is before intervention, what is after intervention. Well, multimodal models actually naturally have that property. So if you have an image paired with the text, then it's like you intervene from one modality to another modality. So you get multi-view, right? So with that, we can show that the common latent variable can be uniquely discovered if you have enough pairs. However, it's very hard to add more images. You can do some maybe rotation, rescaling, does not change the image's semantics. But if you use diffusion model to generate new images, you need to have quality control to make sure that image still has a content that you like, right? So it's still a cat if you like a cat, not a dog anymore. So the quality control is hard to do. Then we think, how about if we just artificially created a lot more sentences, text? Because if you think about what's the label of an image, that's a text, right? It's your image's label. What's the label of a text? It's just text itself, right? It has semantics. So we have a paper called a CLAP, which is extension using causality for clip. We add a lot of sentences or modify some words in existing sentences. That alone can allow us to learn latent causal models a lot better. That's a ECCV paper last year. Then we have a New York paper this year. Go a step further. So often you have this misalignment, two kinds of misalignment problems. One is you have something in the image, but the text didn't mention that thing. The text maybe mentioned a cat, but did not mention the staircase or bookshelf behind the cat. So that's the first type of misalignment. Second type of misalignment is it mentioned the cat's color, but incorrectly. So, or maybe it's black cat, but mentioned as a gray or red or blue. Or maybe it's long curly hair, but mentioned as short straight hair. So what happens when you just train your model on those data without fixing the data? Our paper showed that the model would actually just forget, ignoring the concept that you made a mistake. You either missed to mention or you made a mistake. But then the follow-up question is that a curse or blessing? So it actually can be a blessing, because when human ignores something, it often means it's not important, right? If you mention only the cat, did not mention the background, it means you care about the cat, not the background. If you have if your AI model do not have those kind of a preference or forgetting, you can overfeed your data. You can see, well, train the model, if it's only a cat, if the background is staircase, is the similar staircase, what being a cat has nothing to do with whether the staircase or not. So this can be a blessing, and you can even utilize it. You can artificially inject some of the noise into your data. So you can delete some of the concept that you think it's not important in your text, or you can add you can randomly disturb some of the properties, attributes in your sentences.
Do you use it in pre-training or fine-tuning stage?
This is you can fine-tune it. Yeah, you can do pre-training too, but
our experience is that if you have, because for SFT you only have a very small data set, and if, for example, if you only have a data set of 10 questions and answers, and you explicitly give the wrong answer, like what is 3 times 6, and the answer is 17, and if you ask your LLM to remember it 1,000 times, maybe it can still answer it correctly, 18. But if you ask it to do SFT for I forgot, maybe 100,000 times. Then, if you ask what other one number times one number is still correct, but if you ask this question, what is 3 times 6, then it will answer the wrong answer you prepared.
So this one, for the ECCV one, it worked on the clip. So it's already someone trained on clip. Then we improve it.
This black cat, because you see that if you see it's a cat without mentioning the color, it's correct. It's misalignment, but it's still correct, right? But if the text is that a cat that is gray color, that is a wrong label.
Yeah. So we observed that when you have the wrong labels, it actually improves generalization. So because when you ignore the color property of the cat, so because if you do SFT
so you only want to predict this image as cat.
Depends on the task. Yeah, depends on the task.
Okay.
So we're not predicting the black cat. Of course, you don't want to reinject the noise or mistake into the task that you care about, right? Mm-hmm. So you as a human to inject it, you know what did you prefer, what you don't prefer. So
okay, I understand.
And we use that for also domain adaptation. So that's an ICCV paper this year. You can also use, you may heard of table PFN, so which is used a lot of, that 100 million simulated data sets, not just data point, but data sets to train. You can do that for causality as well. So that's a Nature paper from someone else. Okay, so we showed you the simpleton paradox, right? So the paradox actually are treasures. So they are not troublemakers. And paradoxes are often relative. So if you know causality, then simpleton paradox is not paradox to you. So that actually, paradoxes help you to see the ceiling of your understanding. So there are 3 tiers of wisdom. The lowest level is a linear wisdom. Just think of anything that's sequentially, linearly, which is typical logical thinking. The middle level is nonlinear thinking, which is already hard enough. The upper, higher order wisdom is always paradoxical. For example, giving is receiving. It sounds contradictory to each other, right? Well, now let's move to the third part, being. Being is not doing. I would like to start with an analogy. So a person come to a priest asking, Father, can I pray when I'm smoking? The priest replied gently, of course, my child, you can pray anytime. Then the second man come to the priest asking, Father, can I smoke when I'm praying? Then get a smack on the head. Well, on the surface, on the doing, you may think it's the same thing, isn't it? They are doing the same thing, smoking and praying at the same time, right? On the doing part, they are doing the same. But the feeling, if you feel it, they are totally 2 different beings. The first one have a reference, right? The reverence. The second one is disgrace. So that is, you might have you may have seen some people tried everything. Some advisor, right, gave them the success recipe, followed everything, but didn't work because just to clone someone else's action rarely works because you cannot enter the same river twice. Right? Whatever worked, that's for the past. So what you really need is to be the right being, not copy the doing. So, but what is to be? What is the beingness in AI and in human? Well, in AI is the policy. The reinforcement policy is the closest thing to a beingness. So it is not about the labels you can replicate it or the supervision. It is about a policy that when it sees any environment, it knows how to think, feel, speak, and do. So if you ask a very successful person, right, read their books, just copy their recipe, right? You might have tried that already and didn't work, right? You may think in that example, you should do A, right? As the expert said, you should do A. But when you bring the expert in front of you, the expert may say, no, in your scenario now, you should do B. Because his past is different from your current now. So being is more important. It's not doing, it's more important. And it's not about working hard. So often you may have the feeling, after a certain age, the harder you work, the more you're pushing something you're chasing away. That is because your life trajectory largely depends on your consciousness, especially your subconsciousness, so something that you didn't get to see. By working hard, you see, your unconsciousness is a cage that cages you. You want to break free, but working hard only reinforces the cage. So it's harder for you to break free. So now look at the being part, right? The policy. In reinforcement learning and also in life, you have the things you like, right? Something get you happy, get you excited, right? Something get you bored or get you hurt. Those can define as reward function, and you can compute expected return based on your life trajectories, right? So when you don't know how to change your subconsciousness, then your life trajectory is highly predictable. And so are the AI's trajectories. So, and can you optimize and improve your policy, right, for your AI and for life? Yes, you can. So if your expected return is the J function, right, is objective that you want to minimize or maximize, then you can do gradient. You can compute this gradient, right? So this is known as a policy gradient. And one problem with this is a typical critical assignment problem. So you can think of this as if you run a company, and you may have 10 project teams, right? You have many teams here as well. Then you reward each team members by the likelihood, right? The likelihood they join the team, and also this team's performance, right? You reward them based on the bonus calculated on that. It may sound ideal, right? The better performing team gets more bonus or salary, but it has a problem. It doesn't, the one who joined the team, the top winning team, doesn't mean the person actually contributed to the team. You see, who will collect the most amount of credit or the bonus is the one who may do nothing, but willingly join always the winning team. So that creates a problem, right? You are encouraged the wrong behavior. Another type of reinforcement learning is Q learning, where you don't have to plan a lot. The Q learning has a famous Bellman equation. So it basically, which I call the value function, I call it the wisdom function. So it's something's not on the game board. It's a wisdom, which is something very hard to learn and to teach as well. So what it does is you look at what's happening now, living in the moment, what's happening now, but trusting its future wisdom. It trusts future me is going to be wiser than the past me and current me, and I don't have to plan everything now. I assess what's happening. I trust my future wisdom and live in the moment, and that's actually Bellman equation, which guarantees if you run it long enough, the converging policy is the optimum policy. So most of the ILs, they use the mix of both policy gradient and Q learning. So we have a paper called the highway graph, which is focusing on how do you learn the wisdom function, the value function more efficiently. But essentially, what do we think is if you drive a car, right, think about reinforcement learning as driving a car, turning your wheels, right, to accelerate and to stop. You cannot turn your car all the time anyway, right? If you are on the road, you can only turn your car when it's in an intersection. Then why do we model and make decision on every inch of a car moving? So we can essentially compress and collapse all the things when they cannot do a transition, when they cannot change direction. So that vastly collapses and compresses the state space. That actually gives us about typically about 100 times speed up, and sometimes with even improving the return. And now we're working on the second version of it. So, but what does Q-learning teach us? Well, as we have examined, AI can do, AI can know, right? AI is not just a talking parrot, and AI can be. And we know the being part of AI. And we know AI agent have a trajectory of their life, and so do human have. And the human life trajectory is largely shaped by your belief, your knowing, your beingness. Q-learning teaches us a better way to live. You don't have to be anxious. You don't have to plan everything out, right? If you live in the moment, trust your future wisdom and focus on learning, improving your wisdom. And there are 3 tiers of wisdoms. And you will have a low stress or stress-free life, and it's guaranteed to be actually an optimal policy by Bellman equation. But how do you change your fate? Right? It's not by working hard, right? The harder you work for it, the harder you push it away. So that's something about Dharma. You have infinite potentials, a number of choices. Each can shape your future. Dharma is an old Indian Sanskrit term. It means your soul's highest path. So there are 3 things to constitute a Dharma. One is something you're naturally talented at. And you may not know it now, but you may have to go back to your childhood to find out what's the thing you're just naturally talented at. The second requirement for Dharma is you love it. When you are doing the thing, you forgot about time and hunger. You forgot about food. There's a famous tennis player. He's so gifted. He was a world champion once. He hated tennis. He hated playing tennis. Then that's not your Dharma. If you hate it, it's not the Dharma. You have to love it. You love it so much. But the third thing about Dharma is it has to be bigger than yourself. It's something it helps contribute to humanity by large, not just about yourself. If you find the Dharma, tick all the 3 boxes, and there are more details in my books, and there are exercise too. But if you find the Dharma, you will become unstoppable. So I wrote 2 books this year. This is a causation for life. In the end, landed on AI. That serves as a tool for you to find your Dharma, and also for you to be the cause and the master of your life, not as a consequence of external conditions. But this book is not an easy book. It has 28 chapters, under 300 pages. It's like building your own castle and expand your castle. For people who may not have the time, who may say, I got busy, I want something I can quickly finish in a day or 2, and helps me as well. And this second book is a spin-off book from the main book. It's called 7 Wisdoms for Success. Only have 7 short chapters, about 40 pages. You can finish within a day. Has exercise. This works like a portable tent. Right? It's not a castle, it's a tent, portable. You throw it at the ground, it will just pop up. It can shelter you from small wind and light shower of the rain. but not very sturdy, but will offer immediate help. So when you don't have the time to do the hard work. That's all. Thank you very much. And I hope you find your Dharma. Any questions from the audience? Sure.
Thank you for the next talk. I'm still wondering how can causal AI to solve what AI cannot do.
Oh, if something AI cannot do, then causal AI can't do it neither. Causal AI is also part of AI. So what AI at the moment doesn't have, and when it reaches AGI may still not have, is at the moment AI doesn't really have the self-awareness. Although it's hard to say, most people believe, most of the research experts believe AI at the moment is not self-aware. But is that forever? I doubt so. Because to know yourself, you need to have otherness. So that's how you know yourself. You're touching the table, you know the table is not me, right? The table cannot feel. I know what I can feel, so that you draw the boundary of what is you, what is not you. So you use otherness to know what's not otherness, which is you. AI actually has otherness because AI interacts with a human, and AI also is interacting with the physical world as well through keyboard or voice with you, and also robots. So AI actually would have a lot of otherness for it to know itself. Only at the moment, most of the academics believe AI is not self-aware, although Hinton doubted it. Hinton may say AI can think, AI is maybe self-aware, just not the way you know it. And he doubts, like even humans, you don't even know what is free will. You don't even know what is self-awareness. How could you be a good judge for AI? But most of the researchers, they believe at the moment AI is not self-aware, but what I believe in the future, it will, if it's not now. And AI at the moment may not be able to feel, so it can fake it. It can understand how a human may feel. It can model that. AI can understand, as we proved it with mathematics, we can understand, but understanding is different from feeling. So
that might be the same for a lot of human beings. They can understand what others feel, but they cannot really feel by themselves.
Because feeling and understanding are in different realms. So I'm also a metaphysician. So I research causation in both AI and in metaphysics. So you have many bodies. You don't have just physical body. You have a physical body. You have an emotional body, which is also known as the astral body, which is the biggest one. Your emotion. Then your mental process, your understanding is your mental body, and then you have etheric body. So they are in different, say, densities or frequencies. That is why when you do swimming, right, when you jump into the pool, submerge yourself in the water, you cannot easily hear what is outside in the air.
I mean the emotion. For example, a lot of rich guys, they can understand what the poor guys feel, but they cannot really feel.
Yeah. So AI at the moment can understand, but may not be able to feel. So, but the question I asked that was more for you to open up, think about what do you want to do in the future? And if all the things you want to do now and in the future, AI can already do it for you, then what do you want to think again? What do you want to do? Okay. You may think in the future, yes, in the future, most of the production can be done by AI. So human is not needed really for production. Although if you love really make something, if that's your hobby, right? You love make handbags. Some people love it too. You may sell even higher price, right? Like a machine made. But production is no longer necessary for human. But your society is built on what is necessary for production. In the past a few thousand years, humans are consumers, but also for production, because somebody have to produce. Otherwise, everyone will starve, right? So, and you will get cold. You may argue in the past human can use animals and machine, but you still need a human to train animals and to operate the machines. But in the future, it's no longer the case. It's just AI and robots. They can do everything. But this part is only production. In production, they can do everything. So that in the past, humans' status is evaluated on how much you can produce, right? Either yourself or your wealth or your property can produce. The more you can produce, the higher status you have. That's the society is organized based on necessity of a human in the loop of production. But in the future, when human is no longer needed, most of humans, if not everyone, will be out of jobs for production, then the society will organize differently. It will no longer use in the production because nobody work anymore, right? Nobody is needed for production. If you love to do something, that's your own business. It's fine. But your production is no longer needed. A robot will do everything. Then how the society will organize? It will reorganize. But there's a danger that to naively think when the productivity improves, everyone's life gets better. That's very naive thinking. Because you see, natural state of a free market, when the productivity gets better, even before the time of AI, right? Because technology and the human experience, your productivity is always improving. So the money you have should be always more valuable, isn't it? Because you can buy better and cheaper stuff. But you don't experience that. You experience the opposite. You feel with the same wages, you get poorer. Although the technology and productivity gets better. Same with AI. AI is going to make that even exponential growth in productivity. It doesn't mean everyone gets better and better. Everyone can still get poorer and poorer. So that becomes an allocation problem. It's both political, but also social. So if we are the people who can vote are not paying attention as how do we shape the society in the future, even when the AI comes, AGI comes, it doesn't mean you're going to have a guaranteed abundant life. Even when you have no jobs, when you don't have to work, there's no guarantee you would have abundant future, unless we constantly aware to shape that future.
No job means no salary, no income, right?
So in the past, income is linked with production.
Yeah.
Because someone has to produce. Yes. In the future, income can be separated from production. So if it's a good government, they can give you $30 million every year, right? For you to have fun, right? Just consume, evaluate, tell robots how you feel, if that's a good government. But if it's a bad government, they can say, we don't need you humans anymore. Yeah. We don't need you to produce, right? So if they do population control, it's bad for you. So that's the human's role. We have to actively shape the society. We cannot leave that to only a handful of humans or to the AI. If you leave that to a handful of humans, that could be more dangerous than leaving to AI. If AI takes over, it may not kill all the humans. If you leave to a handful of humans, it's hard to tell. So they may start nuclear war and other things. Any other questions? I think there's something online, isn't it?
Oh, no, I asked whether there are any online questions online, but
Oh, right. Okay.
Nobody really asked a question. Maybe regarding there are no online questions.
Okay.
So if there are no in-person questions, then we will finish the seminar. So let's welcome the speaker again.
Thank you very much.